Aalok will take care of that.
Oh, no. Sandeep is going to take care of that.
Okay, that's fine. But feel free to do it, Aalok, or at least
no. Please.
part of it.
No, please. No.
Okay, as
I'm
you
shutting
like.
up.
As you like. No. Okay, well, so thanks a lot, Aalok, and thanks, Shivaji. And so we move on to the discussion session. We're running about 15 minutes late. We have Davide Gaiotto's talk after the discussion session. And the other thing to say is what we'll do is we planned a group photo since we are coming to the end of this conference after the discussion session, before the last session where Davide will speak. So please do stay for that group photo, which should be about half an hour from now. We'll be a little late starting Davide's talk. I hope that's okay with Davide and all of you. But we hope to get going about 6:45 for that then. So let's get going. I hope many of the speakers are here. I know some of them are not here, but I know that Joao and Enrico are not here. I hope many of the others, no one else wrote to me, so I assume that they're all here. And please turn on your mics and also videos if you can. And the floor is open. We have a very informal discussion here lined up. So go ahead, ask your questions, and let's have a good discussion. It'll be for half an hour, and we'll have to close after that, but maybe enough for you to at least strike up an initial conversation, which you can take forward later. Okay. Anyone who didn't get a chance to ask their questions, would like to make comments, please go ahead. I'm going to look at the hands being raised anywhere. No hands being raised. Everyone's a little tired, maybe. Okay, here we go. There is a hand. 𝗦𝗶𝗶𝗶. Okay, go ahead, 𝗦𝗶𝗶𝗶.
I have a question for Ronak. So, is he there?
Yeah, hi.
Are you there? Okay.
Yeah, I'm here. Thanks.
Yeah. So, what is the final state of the de Sitter universe? If the final state is R equal to 0 manifold, if the final state is an R equal to 0 manifold, isn't the de Sitter just undergoing a big crunch or something?
No, sorry. The final state of the de Sitter is actually an R equal to infinity region. So it's like an asymptotic region, and actually Enrico was really working with that region of de Sitter, for example. The R equals 0 region is off to the side. It's not in the future or the past. It's in the space-like ends. So it's like you should really think of it as, if I may share a whiteboard, like de Sitter really looks like this. This is a hyperboloid, and each spatial slice looks like a little circle, and the circle grows with time. This thing is kind of, in an obscure fashion, converted into that Penrose diagram. So the final state is that.
But in the Penrose diagram on the left, you had R equal to 0, right?
Yeah. So the point is that.
What does that mean?
So these two lines. Where is there? It is. So yeah. Let me just draw the lines. Yeah. So these two lines are R equals to 0. Okay.
Yeah.
And broadly speaking, you should think of those two lines as these two lines. Okay. And yeah. So it's on the side. It's not in the future.
I don't understand what you mean by that, because I would guess that R equals 0 means that the space manifold is just going to 0, right?
Yeah. So here you should think of the spatial manifold as an S0, which is 2 points. So what is R here R here is really the kind of distance between this point and this point. So this is a DS2 I'm drawing. Okay. And in DS3, there will be a circle here, but in DS2, this is S0. S0 is 2 points. So the R is the distance between, this is kind of like R, and R equals 0 is when these 2 points hit each other out here.
Hello.
Yeah,
Anyway.
go ahead. Amitabh, do you want to ask something?
No, actually, I have just a random comment for Ronak. He in one of his last slides, he said something about higher dimensions and
Yeah.
black holes in de Sitter. So I mean, and you were saying that it's important that you should be able to make a distinction between the cosmological horizon and the event horizon. Otherwise, you would not know to which one you are going to under this deformation. I wanted to say that actually this distinction blurs when you are in sufficiently high dimensions and you have rotation. The cosmological horizon can touch the event horizon.
Yeah.
So it's not clear how.
I agree. Yeah. So certainly, and this is also the question. Even in 4 dimensions without rotation, if you're in the exterior of both the cosmological and the event horizon,
Yeah.
there is a certain level of ambiguity where it's not always clear which is which, and so this is why I said that you expect the ADS black hole horizon to sometimes be the cosmological horizon, sometimes be the black hole horizon, and it will depend on quote unquote mood, where we don't know what mood means. Mood presumably means something precise. And yeah, I agree completely. This is the distinction is not very well defined, and this is why there is a question here. Thanks. Yeah.
Okay, anybody else wants to ask a question to any one of the speakers?
Hi, Sandeep.
Yes, Abhijit, please.
If Sandeepan is around, I would like to ask him a question.
Okay, let's hope so. Sandeepan, are you there, please? Maybe it's getting on. I had requested everyone to stay on, but I'm not sure if timings could
Yeah,
work.
I think for him the time doesn't work.
Yeah. You want to ask your question anyway, and we can see if someone else wants to take it up, or you.
Sure.
Yeah.
So Sandeepan talked about this out of time ordered correlation function, and he introduced this notion of extremal chaos, where all the chaos inequalities were saturated, and the function took the form, the correlation, the out of time ordered correlation function took the form that it dipped, and that dip was governed by the MSS bound, the saturated MSS bound, and it came up again and stayed constant asymptotically in time. So I just wanted to understand what this means, that it stays, comes back to 1 and stays constant all the way to infinity.
I see. I see. I don't know if anyone has a comment to offer, or
Yeah,
Arnab has something to say. I'm sorry, I may not see all the hands. Just speak up. It's not a very formal thing. Anyone would like to comment on that, or I'm not sure. Yeah, I don't see anyone.
Okay.
Sorry.
It's
Yeah.
I might be wrong on this point, but based on this paper by Phil Sard, where he studied it in JT gravity, this constant region is what's called the plateau, and basically it's given by a sort of coherent state of arbitrary number of some branes that they don't define, and so it's some extremely non-perturbative thing. I think in their matrix model it was doubly non-perturbative.
Wait, were you talking, what correlation function were you talking about, Abhijit?
I was talking about the standard out of time order correlator that Mardasina Stanford Shankar studied.
That's sort of what I thought. I see.
Yeah.
I know.
I think Phil Sard also.
I know of the plateau regions for correlators of the partition functions.
Yeah, that's this spectral form factor or something, right?
Yeah.
Is that what you were referring to, Ronak?
So this a very similar calculation actually calculates OTOX as well.
I see.
So basically they have to convert. When you take two partition functions into Lorentzian time, you can just put two operators at the top and two operators at the bottom to break time reversal, and this gives you an OTAP actually.
But there, when it comes up, it does not come all the way up to 1, right? It just stays very because it's usually displayed on the logarithmic scale, and it's much less than the initial value.
Yes.
But in his calculation, it somehow went to 1, and then he defined the spectral presentation, and it seemed like even if you use any density, this property should be universal for any sort of spectral representation. So it seemed like a universal property. That's why I wanted to understand what it means and so on.
I see. Yeah.
Hi, Abhijit. Can I make a very
Arnab, go ahead. Sorry.
Yes, sorry. I mean, I don't really have anything very specific to say. I'm not sure if what I'm going to say is actually either correct, but nonetheless, I mean, I think in some sense, what seems to be expect, of course, these correlators to start from somewhere, have a non-trivial dynamics, and then decay to 0 and stay 0 forever. I mean, that's the usual story. But what Jnandevan seems to be suggesting is something similar to what would happen if you could access, let's say, the Poincare recurrence time, because then the system would again, reproduce, go back to your initial state, and you could actually collect everything. So to me, it sort of looked like that. But I'm also very confused by it because the time scale at which it happens is slightly after the scrambling time, which is again not what you would normally expect it to see. I mean, right? I mean, it's like doubly exponentially large. So I'm not really sure what to make of the fact that it actually goes back all the way up to where it started from. In fact, I'm also not sure even if it did not go all the way up to the starting point, even if it were staying somewhere non-zero and staying flat for forever essentially, I would not quite know how to interpret that either. But I mean, anyway, it's just a comment, and maybe Jnandevan, if he was around.
The scrambling time is a lot shorter than the Poincare recurrence.
Yeah. Of course.
That's I see. And it was going back up, you say, on that kind of time scale.
Yes, it's going back up. I mean, for example, it's going back up even much before the Heisenberg time, which is what you could access otherwise, right? Heisenberg time is when you would start to see all this deep ramp plateau kind of structure happening.
No, but actually, Jnandevan had a flexible parameter. I mean, it was just a solution to some constraints that he had.
Right.
It was parameterized by a solution which looked like that. But the scale at which this happens is something that he could control.
Correct.
It was just a parameter in his solution.
Correct.
So one could get around what you are saying by saying that that tau effective or whatever scale is very, very far, right? So in that sense, you could push it very far off into time. But nevertheless, what was definitive was the coming up at one part.
Yeah. I mean, my confusion is that you have no a priori way of saying that this parameter need to be tuned so that it has to be pushed very far, right? I mean, you could also have it happening right at the scrambling time scale, which would be very confusing because, well, at least, I mean, okay, to be honest though, I mean, in that treatment, there's a small parameter which is not quite specified. So it kind of depends on what that small parameter really is physically. So for example, when we do this calculation in CFT, large C or whatever in holography, etc., we always stop at the first order. We don't even begin to see what Jnandevan was describing because we don't have a small parameter on top of it. So maybe if we have a small parameter, which is, in some sense controllable, and then on top of that can do this kind of calculation, then maybe it's natural for some reason. So for example, one thing that I had mentioned, although this connection is not really as sharp as probably one would like, but nonetheless, there's a similarity in the sense that if you have these 2D CFTs and if you do this, strip calculation with some inhomogeneity in the boundary, etc., some by hand introduced small parameter in the system, then actually you could design that perturbation in such a way that all, at least some of the subleading constraints that Somdeepan was describing could be saturated. So, so this curve going back up would need a resummation of all of those. But I'm just saying that it may not be completely, exotic or out of, completely crazy to think about such a situation where you have a small parameter. But I do not know of a good example of a small parameter. The thing that confuses me a lot, not confuses, but I don't quite know how to do it, is because having weakly coupled theories is not really good. Weak coupling is not going to give you this. So this is something else. And yeah, I don't, as I said, I don't have anything sharp to say, and probably Somdeepan could have clarified this.
Sorry, one comment about this: the computations that Stanford and company did, Stanford and Schenker and company, in the Eikenall approximation, don't show this.
Sorry,
do not.
Yeah.
It just, the way it goes is that it's like 1/1 plus exponential growth, their answer, with a small parameter behind, G Newton behind. So if you expand that in a Taylor series expansion in G Newton, you get 1 minus G Newton times exponential growth.
Yeah.
And but if you look at the whole function, it's 1/1 plus G times exponential growth, just decays forever. In Eikenall approximation.
Okay.
No, that is right. That is right. So 1/n expansion, any result in large n theory in a 1/n expansion will not probably give you this, will not make the OTOC rise again.
No, this is not 1/n expansion. This is just large Eikenall approximation at large times.
Yeah.
Looks like the function is just decaying.
I guess, yeah.
No, but it's also large n, right?
It's G Newton. I guess you meant in 1/, there's a G Newton suppression there to that term.
Yes.
Okay, right.
It's also a large n result.
Okay, let's see. Anyone else who hasn't asked anything yet on any other speakers, or even for someone? Let me see. We are going to do the following, if you don't mind. Davide's talk has already been pushed 15 minutes. So we'll close at 6:40 and have a group photograph. That will take about, few minutes to organize and so on. And then we move sort of at 6:45 at least onto Davide's talk. So we don't push it by more than 15 minutes. Okay. So, but we have to keep ourselves entertained. I'm not letting you guys go before that, for one thing, simply because all of your photos are most important. So let's see.
I have a question for Siddharth.
Okay, go ahead. Ask your question, and Shomdat has another. Ask it. Go ahead, please, Amitabh.
Yeah, no, actually, I have already clarified this, but just to discuss this, I have clarified this with Siddharth on chat, but just to discuss in the.
Please.
Yeah,
we can all benefit. Yeah.
So you showed this symplectic 2 form, and you said this is a proposal for your symplectic 2 form. So can you comment on that? How it relates, how it comes from the Lee-Wald symplectic form and things like this?
Right. So I said it's a proposal because we motivated it by calculating the charges from the Bondi mass solution equation, and it matches with those charges. If you were to compute it from the bulk, if you were to compute it using a bulk symplectic form and a Cauchy slice and pushing that to null infinity, then we see that this redefinition of ours, together with our fall-off conditions and so on, they take care of most of the terms that come in this computation. But we have still not taken care of one class of divergences that come up, which are really just which come up because of these CABs. So since the CAB, which is U independent, there are some terms in that bulk symplectic form which are just pure functions of those CABs, and and those being U independent, once you integrate over U, they give you some divergence. So that's the reason I didn't talk about deriving it from the bulk.
Yeah.
So but I do think that we'll probably be able to cure those divergences by some renormalization of the procedure.
Yeah. I mean, as I was telling you on the chat, recently there have been many papers, and you know very well, recently there have been many papers on this renormalization of the symplectic 2 form. And perhaps those things can be used to fix this divergence.
Absolutely. So there was this paper recently that talked about doing about implementing holographic renormalization for asymptotically flat spacetimes. And they have a procedure they claim which will enable one to write down finite symplectic forms for asymptotically flat spacetimes, and they carry through their procedure for d equal to 4. So my guess is that if one were to do that for higher dimensions, then one would be able to solve this issue.
Yeah, thanks.
Thanks for the question.
I have a question for Siddharth.
Go ahead, show him that.
For d equals 4, I thought there was some kind of vanishing of some coefficient, right, in the equation for the CABs. Is that correct?
Right.
Yeah. So is that the reason that the straightforward analysis in d equals 4 is not easy or something?
No, but no.
Because you did it for d equals 6, so that was what I was wondering about. Why you didn't do it for d equals 4? Right.
So the point was that so in d equals 4, CAB was playing 2 roles. So the U derivative of CAB gives you the new tensor, and that was giving you the flux of gravitational radiation. And it was also in CAB in any dimensions gives you the soft charge, because it's symplectically paired with the operator that gives you the soft charge. So what is happening was that this vanishing that I showed, which if you looked at the AB component, the Einstein equation, there's a d-4 that comes out, and then you get a del U CAB. But that itself is not special to 4 dimensions, because in any dimension there is a particular CAB, the one which corresponds to the radiative fall-off, whose U derivative is not fixed. So for 4 dimensions, it happens to be the same CAB that gave you the soft charge, and so that is a coincidence in some sense, that in 4 dimensions both these fields are the same. But the fact that something del U, you have a particular del U of some particular CAB vanishing, that is true in any dimension, and in any dimension there is one particular CAB that does that, which as I was saying is the one that gives you the radiation.
So the coefficient multiplying the del U CAB, that entire term vanishing doesn't create any problems.
No, that doesn't create any problems. And in fact, we need that, because if it didn't vanish, then we would be in trouble, because then you would not have then we would be wondering where radiation is coming from at all.
Okay.
Okay, very nice. I think let's wrap up the discussion just a little bit early so we can move to our photo. Now, what I'm going to request is all of you, before we do that, because it's Friday evening, we have a very important last session coming up, and you all, I am sure, are waiting like I am for Davide's talk. But just before that, let's do 2 things, if you don't mind. We'll thank everyone after Davide's talk, but let's do that because a few people might be wandering off or whatever. So what I want to do is just thank on all of our behalf the organizers now, and we come back and thank them again formally at the end, but some of them are filtering off, so I thought let's do that. So please, all of you, just open up your videos and let's thank the organizers, and after that let's take a group photo and then let's move to the talk. Okay, so first of all, join me in a huge round of applause for all the organizers, please. Thank you. I want to thank especially Aalok Misra for really being the helmsman of this whole meeting, the National Organizing Committee for all the work you all did, and the choice of excellent speakers, all the speakers, the audience, which is most important, especially online, to keep your attention and ask your questions, etc. And all the organizers in Roorkee, the AV team, and especially I want to thank 3 students. I hope they are here. Please turn on your videos. Mohak, Lucky, and Shubham, are you there, please? I can't see who is who, but I hope you're there. And a special thank you to you all from all of us. Aalok has told me how much you have done, and we are all grateful to you for having worked day and night and made this conference such a big success. So thanks again, Aalok, your whole team, and everyone for a wonderful, wonderful meeting. I'm now going to hand over to Aalok to organize the group photo. Aalok, are you there?
Yes, thanks. Thank you so much, Sandeep. With your permission, I just wanted to thank one particular individual. Can I, with your kind permission?
Yes, of course. I'm sorry.
So I would put it this way, that if any one of us ever thinks of having an NOC, you need to have one man on that team, and that person is Sunil Mukhi.
Okay.
And I'm so grateful to Sunil. I really have no words. I mean, there are so many things that I have been asking him. I don't know what they call it, offline, online, everything is online, but I mean, and he has been so precise, so prompt, and so objective about everything. I mean, I'm so grateful, Sunil. Thank you so much. Really appreciate it.
Sunil, come on video. I can't see you.
He is.
Here he is. Okay. All right. Congratulations. Thank you, Sunil. I mean, I think we all know that what Aalok has said is absolutely true.
Everyone pitched in. I think I don't think I really did much. Alok took all the stress, and his team, I think, did everything. So
no, I'm sure you did a lot. Thank you. Thank you very much. Aalok, also please thank IIT Roorkee administration from all of us for allowing us the use of all the facilities and the beautiful backdrop, which we hope to visit in person.
Yes.
Looks like the White House, as you said, but I think it's more impressive.
That's what students call it.
Looks much more impressive. Okay.
So I think can I take that group picture? It's going to be
please. And then we'll move on.
Okay. So there are 3 screens that I see. So I'm going to do it. So this is 1. I do see some who would still turn off their cameras. Maybe if possible, they could kindly turn it on. Maybe not. Okay. That's screen 2. And then the final screen 3. Again, I request maybe can we all turn on our cameras? Really appreciate that. Just a moment. Sorry. Just a moment, please. Yes, we're all done. Thank you so much. Thank you.
Thank you, Aalok. Thank you very much. So, Aalok, is it okay if we move on to
absolutely
Davide talk now?
Please. Yeah. Sorry, okay. Davide. Apologize. Sorry.
Yeah, Davide, are you here?